So recalling the basic definition of a function, I like to think of it as a series of operations performed on a given quantity or variable. So for instance, the equation g represents the operation of taking the absolute value of a variable in this case. So composite functions represent the function of a function, meaning you can keep building larger and larger functions by plugging one into another. So this means we're increasing the number of operations that we're performing on the variable. So in other words, the idea is that instead of substituting a numerical value in place of x, you can replace x with an expression. So you could plug an expression itself in place of x. And so on, and build more complicated functions. So anyways, a classic example would be, suppose you have the area of a circle. So area as a function of r, the radius, would be pi times the radius squared. But suppose, or let, r be a function of time. Suppose it's t plus 2, for example. So in that case, there's an alternative way to represent this using the notation for function composition, a little circle. We could say a is a function of r, which is a function of t. So again, this indicates that a is a function of radius, but radius is a function of time. Therefore, ultimately, area is a function of time. How can I write this? Well, pi, and then in place of r, I substitute the expression t plus 2 squared. So again, suppose you have a circle. Perhaps you have like an oil spill in the ocean, and assume it's modeled by a perfect circle. As time increases, as t changes, in response, the radius increases. And as the radius increases, the area of the circle increases. Let's see if we can do another example. Another classic example would be, again, related to volume or area. Suppose you consider the volume of a sphere, which is 4/3 pi radius cubed. And again, let r be a function of t. Suppose the radius changes according to the expression 2t plus 5. Then the volume could be represented in terms of time. 4/3 pi. Again, the idea is that I'm replacing a variable r with an expression. So I replace r with 2t plus 5, and it's cubed. And that's simplified. I could leave it in that form, but if you wanted to FOIL it, I could represent this as 2t plus 5 times itself 3 times. Foiling the first two binomials, I get my first times my first, 2t times 2t is 4t squared. My outer would be 10t. My inner would be 10t. So that would give me 20t, And then multiplying my last terms, 5 times 5, gives me 25. Multiplied to my last binomial. Distribute 2t to each term. 4t squared times 2t gives me 8t cubed. 20t times 2t, 40t squared, plus 50t. Good. Now distribute the 5. So I get 20t squared. 5 times 20t gives me 100t. 5 times 25 gives me 125. Combine like terms. My squared terms, my t terms. So I could also express this as 8t cubed, 60t squared, 150t, plus my constant. And I can write that expression in place of 2t plus 5 cubed. But anyways, let's look back at the original problem. So let's see how we can build some more complicated functions consisting of more operations on our variable. We have an absolute value, g, a rational function h, and the greatest integer function f. So suppose I'd like to find f of h. Oh, one more time, let me just show what this notation means. Let me do f of g. I'm just going to do a random example. Again, the meaning of this notation is f of g of x. So the little circle does not indicate multiplication. Rather, it actually signifies a function of a function, the composite function, plugging in an expression in place of a variable. And again, so in this case, this is what I do first. This is my inner function. Whereas the outside portion is my outer function. And this is why this topic is important for pre-calculus, because now it is kind of getting into some ideas that we will, or some terminology that we'll use in calculus, like the idea of an inner function and an outer function. That's why it's relevant. Also at times, again, when we wrote area, for example, as a of r of t, sometimes the innermost variable, t, is what area would ultimately depend on. This is called a parameter. And of course, it's also an independent variable. Whereas since r changes in response to t, this is our dependent variable. Okay. So now, yeah, this is becoming like a whole little lecture or a lesson. Usually I just do the problems. So yeah, we're still using that notion though, that we learned in Algebra 1 or Algebra 2, independent variable versus dependent. But now we're using terminology such as inner function and outer function. So that's all the terminology, the theory. Suppose you'd like to find f of h of 3. Again, this does not mean multiply by 3. The little circle does not mean that, nor does the 3 on the outside. Instead, f of h of 3, off to the side, h of 3 would be 1 over 3 squared is 9. Yeah, because I'm plugging it in here into equation h. So I guess I'll show my work the first time. 3 squared minus 4. Or 9 minus 4, which gives me 5. So f of 1 over 5, I find equation f, greatest integer of my x value. 1 over 5 is 0.2. Oh no, there's a little spider that's hanging above my screen right now. Oh, that sounds so random. Anyways, greatest integer function of 0.2 gives you 0. And that's how you'd calculate the greatest integer function for your composite function. Let's do one more. I want to keep the original equations on the board still. So suppose you'd like to find g of h. I'm so afraid of spiders. G of h of 1. That'd be g of h of 1. Okay. H of 1 would give us 1 over 1 squared minus 4 is negative 3. Find equation g, replace x with 1 over negative 3. Equation g says take the absolute value of your number, which gives positive 1 over 3. Good, and then I'd like to do just one more example. Suppose you have h of 0. So I write this as an extra set of parentheses. I calculate the inner function first, which is h of 0, which becomes 1 over 0 squared minus 4. So that becomes 1 over negative 4. So again, I find equation h, but I'm going to replace x with 1 over negative 4. So finally, that's 1 over my x value, 1 over negative 4 squared minus 4. This is 1. Once I square my fraction, I get positive 1 over 16 minus 4. I'm going to write that 4 as a fraction multiplied by 16 over 16 to get a common denominator. Finally, this becomes 1 over 4 times 16 is 64. So we have 1 minus 64. So negative 63. Now 1 over means take the reciprocal, flip the fraction. So your final answer is 16 over negative 63. So notice how I can do a composite function consisting of h and itself. So I'm plugging, a function into itself. But it does not mean I'm taking equation h and multiplying it to itself. And that's what it means to be a function composition. We're plugging an expression in place of x, or a number still, in our inner function.